Okay, replacement reactions. In contrast to synthesis, combustion, and decomposition reactions, many chemical reactions involve the replacement of an element in a compound. So taking one thing out and putting something else in its place. Replace, take something out, or do it again, place something different. There are two types of replacement reactions: single replacement reactions and double replacement reactions. Single means one, double means two. Now that you've seen how atoms and molecules rearrange in synthesis and combustion reactions, look closely at the reaction between lithium and water that is shown in figure 10.8. The expanded view of the reaction at the molecular level shows that a lithium atom replaces one of the hydrogen atoms in a water molecule. So here is lithium, and here is the OH negative, and it's releasing hydrogen, and the lithium is in here with the OH. So the following chemical equation describes the activity. 2 lithium and 2 water react to produce lithium hydroxide, I think hydroxide, and hydrogen. A reaction in which the atoms of one element replace the atoms of another element in a compound is called a single replacement reaction. So you have an element and a compound, and they react to produce a different compound and an element. The reaction between lithium and water is one type of single replacement in which a metal replaces a hydrogen in a water molecule. Another type of single replacement reaction occurs when one metal replaces another metal in a compound dissolved in water. For example, figure 10-9 shows a single replacement reaction occurring when a spiral, this is a spiral right here, of pure copper wire is placed in an aqueous silver nitrate. So in the water silver has been dissolved in the water, and a silver nitrate, and it has been dissolved in the water, and then they put a copper metal wire down into it. The shiny crystals that are accumulating on the copper wire are the silver atoms that the copper atoms replace. So the copper is reacting, and now the silver is becoming is reacting here. So we have copper and silver nitrate, yes, react to produce silver, a solid. So this is becoming silver, solid silver, and copper nitrate in the aqueous solution. A metal will not always replace another metal in a compound dissolved in water. This is because metals differ in their reactivities. A metal's reactivity is its ability to react with another substance. In figure 10-10, you will see an activity series of some metals. This series orders metals by their reactivity with other metals. Single replacement reactions like the one between copper and aqueous silver nitrate determine a metal's position on the list. Here's the list. Okay, the most active metals, those that do not replace the metal in the compound, are at the top of the list. The least reactive metals are at the bottom. You can use figure 10.10 to predict whether or not certain reactions will occur. A specific metal can replace any metal listed below it in a compound. You cannot replace any metal that's listed above it. For example, you saw in figure 10-9 that copper atoms replace silver atoms in a solution of silver nitrate. However, if you placed a silver wire in an aqueous copper 2 nitrate, the silver atoms will not replace the copper. Silver is listed below copper in the activity series, and no reaction occurs. The letters NR, no reaction, are commonly used to indicate that a reaction will not occur. The silver will not react with the copper nitrate in an aqueous solution. So it's no reaction, okay? So potassium would react with iron and replace it, but iron would not replace potassium, okay? The Chem Lab at the end of this chapter gives you an opportunity to explore the activities of metals in the laboratory. A third type of single replacement reaction involves a replacement of a nonmetal in a compound by another metal. Halogens are frequently involved in these type of reactions. Like metals, halogens exhibit different activity levels in single replacement reactions. These reactivities of halogens determined by a single replacement reactions are also shown in figure 10.10. The most active halogen is fluorine and the least active is iodine. The more reactive halogen replaces the less active halogen, and that is part of a compound dissolved in water. For example, fluorine replaces bromine in water containing a dissolved sodium bromine. However, bromine does not replace fluorine in water containing dissolved sodium fluoride. And here is the chemical equation to show it. The problem-solving law below will help you to relate periodic trends of the halogens with their reactivities. And here is the problem-solving lab that you can look at on your own. And here are some example problems for you to look at on your own. All right, the final type of replacement, so this is our last one, double replacement reactions involve an exchange of ions between two compounds. Okay, this is a compound and this is a compound. This is different than up here where we have an element with a compound, right, in a single replacement. So the double replacement requires two compounds. In this generic equation, A and B represent positively charged ions. The cations always come first in the chemical compound name. And X and Y represent negatively charged ions, anions. They come second in the chemical compound name. As you can see, the anions have switched places and are now bonded with the other cations in the reaction. So it was AX and now it's AY. It was BY and now it's BX. This is a double replacement. Two things are replaced. More simply, you might say that the positive and negative ions of two compounds switched places. The reaction between calcium hydroxide in an aqueous solution and hydrochloric acid is a double replacement reaction, calcium chloride and water. The ionic components of the reaction are calcium and OH negative and hydrogen and chloride. Knowing this, you can now see the two replacements of the reaction. The anions, OH and Cl, have changed places and are now bonded to the other cations, Ca and H, in the reaction. The reaction between sodium hydroxide and copper chloride in solution, the reaction between sodium hydroxide and copper 2 chloride in solution is also a double replacement reaction. Okay, here again we have a compound plus another compound, and they react to produce two different compounds than the ones they started with. And that is because they're negative ions, the anions, are moved to match the opposite cations, right? So you see the OH is with the potassium here, but the OH moves to the copper, okay? I'm sorry, sodium, not potassium. In this case, the anions, OH and Cl, change places and are now associated with the other cations, sodium and copper. The result of this reaction is solid product, copper 2 hydroxide, okay? A solid produced during a chemical reaction in solution is called a precipitate. Notice we have an aqueous solution and an aqueous solution that yield an aqueous solution and a solid. This solid is called a precipitate, okay? Precipitate, something that comes out. Think about precipitation, that's rain or snow. It's something that comes out of the atmosphere. And this is a solid that is precipitating out. It's called a precipitate. It's a solid though. One of the key characteristics of double replacement reactions is the type of product that is formed when the reaction takes place. All double replacement reactions produce either a precipitate, a solid, a gas, or water. An example of a double replacement reaction that forms a gas is that of potassium cyanide and hydrobromic acid. Must be potassium cyanide and hydrobromic acid, and they react to produce an aqueous solution and a gas. It is important to be able to evaluate the chemistry of a double replacement reaction and predict the products. You have to be able to predict what's going to happen if you see two things coming together. The basic steps to do this are here in this table, which I'm going to let you look at. The steps, you can look at those steps on your own. Then you can do these practice problems. Now that you've learned about the various types of chemical reactions, you can use table 10.3 to help you organize them in a way that you can identify each and predict its products, okay? So here are the different kinds of reactions that we've already studied. Here tells you about the reactants, what's going to go on the left side of the arrow. And here are the probable products, what's going to come on the right side of the arrow. As the table indicates, the components of the double replacement reactions are dissolved in water. Okay, two compounds dissolved in water. As you continue in section 10.3, you will learn more about double replacement reactions in aqueous solutions. Aqueous solutions means dissolved in water. Okay, some assessment questions for you. Hope that helps.